Okay, we're about to look at one more way that we can actually calculate these enthalpies of reactions. And these are actually based on tabulated values also, but not the same table that was on 367 of our textbook. It's actually a different table, and it's based off these things we call the standard enthalpies of formation. So well, these standard enthalpies of formation are shown below, and the calculation for this is fairly simple. It's the sum of all of the standard enthalpies of formation times their stoichiometric coefficients for the products minus the sum of all of the standard enthalpy of formation times their stoichiometric coefficients for the reactants. And so if you look right here, I just got an example of all these delta H of formation. Now, one of the things that's interesting about this is these are all on a kilojoule per mole, and they're actually specifically per mole of product form. And it's not talking about this product here, but it could, or excuse me, this product there, but it's actually talking about both these two things being formed from in these enthalpy of formation reaction. These values, unlike the values from the bond enthalpies, which are always positive, these values can be positive or negative. Because sometimes when you do these enthalpy of formation reactions, you end up getting a negative value and exothermic reaction. Sometimes you get an endothermic reaction, and you'll see why hopefully on the next slide. But then the other thing is that there won't be any elemental enthalpies of formation. They're always going to be zero for these things. And if you looked, say on the, well, we won't go back to it, but on the table, again, that 367 in your textbook, there are things like H2 on that table that actually have 436 for the value. And that's because those are the amount of energy involved in that hydrogen-hydrogen bond. But in these cases, H2, the delta H of formation for H2 gas would actually be zero. So why is that? Well, these enthalpies of formation are a very, very defined set equation, chemical equation. And it's defined as making 1 mole of product from the elements in their elemental form. So what's the elemental form of H2? Well, hydrogen, it's H2. Elemental form of oxygen is O2, both in the gas form. That's their natural state. And so to make this right here, to make the water right there, from the elements in their elemental form, the chemical reaction would look like this. Notice we got a 1/2 right here. Enthalpies of formation are one of the few places where we're allowed to have half coefficients, 1/2 coefficients. Now looking at these things, and remember these are all on a kilojoule per mole of water form, so you can have half a mole of oxygen, right? But of course you can't have half an oxygen molecule, that'd just be an oxygen atom, and those things, they always bind with other oxygen atoms. Delta H of formation is negative 241.8. So if you're looking at these or trying to identify heat of formation reactions, make sure that the elements are just by themselves in the correct state. Hopefully you'll be able to identify what the correct state is. Like if you see H2 solid, you'd be very, very cold. That stuff is extraordinarily cold, actually. You probably won't ever see that hydrogen gas as a solid. Anyway, so but remember, it's not. This is just one of those delta H values that you might have. So if you have this, right, this would be one of these delta H values. You'd have to multiply by its coefficient. So let's look at an example of this. Oh, the formation refers to it forming directly from elements. So that's where that formation term comes from. So just some examples of chemical reactions that are and are not formation. This is a formation reaction because we got carbon solid, oxygen gas, going to make CO2. This is a formation reaction. This down here is not a formation reaction. Oh, wait, I'm sorry. This is a formation reaction too. Then we got a couple of examples or one example of a non-formation reaction, right? We don't have elements on the reactant side. We're not fully forming 1 mole of product. By the way, if I were to write H2 plus O2 goes to form H2O, and put the right states on it. We got gas, we got gas, and we got gas. And then put a 2 right there and 2 right there. This would not be a formation reaction because it's defined as 1 mole of product. Formation reactions always have to make 1 mole of product and then use whatever coefficients you need for the reactants to make it a balanced chemical equation. So how do we use these heats of formation? Well, we look them up in tables. We look the actual heats of formation for the different chemicals up in tables, and then we multiply them by their stoichiometric coefficients. So we would look up CO2, multiply by 3, H2O, multiply by 4. And remember that in this case, it's always products minus reactants. Now think about the bond enthalpies, right? That was the products or the reactants minus the products in a sense, because it's bonds broken minus bonds formed, right? Bonds broken are positive values because that's an endothermic process. Bond formed is an exothermic process. So looking at this, going to plug in some numbers. We'd look up on our tables, find out, oh, well, here's the sum of all the positive or the things we're going to add together minus things we're going to subtract. One other thing that makes this complicated, though, is some of these heats of formation are negative themselves. And so we look these up in the table. Appendix 4 in the back of your textbook will actually have that. And so you'll have 3 times negative 393.5 kilojoules. That's the value for CO2 in the gas phase. Then we have water, negative 285.8 kilojoules. Why are we able to do this? Why does this allow us to get the delta H for this overall reaction? It's again because of Hess's law. Remember, the enthalpy is only dependent upon the final products and the beginning reaction. It's because it's a state function once again. So once again, just like in the bond enthalpies, we're using Hess's law to do this. If we work out the math all the way down, it looks like that right there. I'm going to leave it for a second, but you remember you can pause the video. Now there aren't a lot of tricks to this, but doing all this math all the way through correctly does take a little bit of setup. So what I would suggest doing is, instead of after you get this bit right here, if you're just starting right there, you plug all that into your calculator, do it in steps, right? Do 3 times this, write that sum down, or that multiple down. 4 times this, write that down, with the correct sign. Remember also that this thing gets distributed through, so this value would be positive, and that value, of course, would still be 0, because 5 times 0 is 0, minus 0 is still 0. So we have all those values going through, and there's your calculation. So go ahead and try out Chem 101, problem set 7. Remember, chapter 10 still. So, and I'll see you guys tomorrow during the conference.